Okay, so next speaker will be Dr. Joost Venrooij. I wouldn't like to be too long to introduce him, but I remember when we were at Max Planck Institute, where he has got his PhD, and even at the end of the PhD he was already reviewing DSC papers, and so very quickly he's got in the DSC Scientific Committee. Well, I give you the floor and just explain how the BMW Driving Simulation Center is working to let us know some lessons and to do better what we do today. Thank you. The floor is yours.
Thank you. Thank you, Andras. Hello, everybody. It might not be a big surprise, but I will be talking about driving simulation. But what is new is I want to talk about the visible and invisible development work that drives it. Now, we at BMW are convinced that with driving simulation we can develop our products faster and better. And based on this vision, BMW's Driving Simulation Center was built. It houses 14 different simulators, ranging from very small static facilities up to very large driving simulators, up to 400 square meters in size. The center is really quite unique, and the big opening was exactly 4 years ago at this very conference, the Driving Simulation Conference 2021. Some of you might remember visiting the center back then. We have been operating it ever since, and today I want to use this center as my stage. I want to use it as a backdrop and talk to you about what it took to bring this center to life. So which challenges did we face, and which innovations, both big and small, were required to achieve our goals. Now, what are our goals? What do we want to do? The Driving Simulation Center services many different types of use cases. Today, I want to focus exclusively on this one, virtual driving dynamics development. Here we see some impressions. That's something we typically do with real vehicles on real roads. And the goal here is to evaluate and select components, tires, dampers. It's really all about mechanics. And I want to virtualize this. We want to bring this on the simulator. Why? Well, you can imagine that we imagine some benefits. You see them listed here on the right. And what you can also see is that this is not a new slide. I presented exactly this slide 2 years ago. And today I want to address what happened since. So we imagine we have a new center with 14 brand new simulators, and we have this use case we just saw, right? So what happens next? What does the road look like from here? Well, you might say, how hard can this be? You just use the simulator and you do this use case. The road might be long, but it's straight. In reality, the road is more like this. The first thing to notice, there is no road. If you want to go somewhere, you have to create the road yourself. That means up the hill, through what looks like a snake-infested jungle swampland, and our use case is somewhere behind those hills. So I would like to tell you about what we learned on the way and whether we have achieved our goals at all. Now, a lot has happened, so I would like to bring some structure to this talk, and in order to do that, I would like to introduce you to this model, the technology maturity model. We have based it on our experiences in the Driving Simulation Center, but it can be more broadly applied. Luckily, it's rather simple. It has 3 words: functional, meaning that a technology basically works. Usable means that a certain group of people can start to use this technology productively. And then finally, beneficial, which means that we have something that we didn't have before. We finally have a benefit. We can do something better than we could before. Now, a few important remarks. First, most technology stays in this functional phase. There's maybe a prototype, maybe a paper. If they're lucky, they're presented at conferences like these, but they will never be really usable or beneficial, and that's fine, right? Not everybody has to be bothered by actually going through these phases, but we do. If we are serious about those goals I just mentioned, cost reduction, flexibility increase, we have to progress all the way to the right. Now, the second message, and the most important message of this entire talk, is going through these phases is a lot of hard work. And this is work that is very often not seen and also, frankly, underappreciated, and that's why I want to address it today. Now, I've selected 3 things I want to talk about per phase. Why 3? Because that's all we have time for. So let's get started. I have collected everything regarding functional development on one slide. That's not because that's less important than the rest, but that's because this is something we do well. This is something we know. This is all published work. What do we need to bring our use case to life, right? Well, we need at least these three things. We need high quality input, and for our use case, that means high quality vehicle models. We use multi-body simulation for that. These are very complex, but also very high fidelity models. 2 years ago, I presented at this conference something about our work in this direction. Back then, the novelty was that we could include very complex, flexible body parts. A lot has happened since. I will not go into details here, but the point is that we have put a lot of effort in getting the input for our use case right. Then we need high quality output, obviously. In our case, that means good simulator motion. That's in the end the signal that our experts use to evaluate the components and do their work at the simulator. Now, we need good simulators for that. We have a bunch of those, but we also need good control. And we at BMW have been working on our own motion cueing algorithms for a long time. You actually might have seen some of our work this morning. And we're really confident that we can do this in a good way. But in order to be sure, we have to validate this, the final part. We noticed very quickly that there are, or were, no standardized ways of doing this. So we decided to develop our own. We have engaged 2 excellent PhD students to work on this, dedicate their entire time to this. Unfortunately, today, I cannot give their work the attention it deserves, but both Chantal Himmels and Maurice Kolf are both here. If you're interested in their work on validation or evaluation of motion cueing, don't hesitate to contact them. So, with that, we have achieved a very important step. We have implemented a functional use case. And as I already mentioned, most presentations end here. Again, that's fine, but today, just once, I would like to look ahead. What happens then? How do we make this this functional use case in a usable and hopefully a beneficial one? First, we need to scale it up. In the beginning, our use case was a one-off. We had one model running on one simulator in one scenario, and about 4 people in the company that knew how to operate this. Now, in order to use this, we need to scale this up, use case expansion. Obviously, that's a lot of work. But more importantly, it also creates new problems that weren't there before, like data management. So once we were able to create a lot of new MBS models, the question became, how do we make sure that the right model ends up at the right simulator and the right level of quality? Basically, with use case expansion, a big challenge is how to do this without losing track of what is going on, what you are doing, what others are doing. That is a big challenge. And I speak from experience when I say that this has risks. And scaling up too fast might mean that at some point everything breaks and nothing works properly. So it really pays off to have a good strategy for this. So once you have a proof of concept working, it's really recommendable to think about a strategy to do your use case expansion. And sometimes it might mean that you have to scale down or limit your scaling up in order to fix other problems first. And that brings me to my next point, robustness. If I would have to select one challenge, the biggest challenge in operating our new driving simulation center, it would be this, robustness. Robustness means that every single component of your system works every single time. And if you have a lot of components that can fail in many complex and poorly understood ways, then this is a real challenge. And here I have an example of a robustness issue we were facing. In the beginning, we had the problem, this is our diamond space simulator, our highly dynamic simulator. We do high-speed slaloms here, amongst other things. And we had the problem that sometimes our MBS models would crash. Or actually, they would first explode, and then they would die. And that led to quite violent simulator motion, as you see here. That's 23 tons of simulator mass that comes to a sudden stop. That's really no fun. This is a problem we had to fix. And we fixed it. We worked on our model robustness. We implemented new features called crash detection. But the point here is that in order to make your technology usable, you have to address every single robustness issue, big and small. And this is unfortunately very time-consuming, but also a very frustrating affair. It takes a lot of time on your simulator just to identify and fix problems. This is something that also management should be made aware of. But again, it's absolutely essential to do this. Robustness is a very essential part in making your technology actually usable. Then we also need to talk about responsibilities. In the beginning, we were a very small team, very agile. We could do a lot of things on the fly. But once we started to work with this use case productively and the amount of people that were involved grew, it became clear that we had to talk about who does what by when. And that's logical, obvious. You have to at some point think about this and write this down, and that's where you can make workflows like you see here. But we noticed a few things. First, it shouldn't be underestimated how much work it takes to write a workflow like this. It turns out that people have very different understanding of their own responsibility with respect to somebody else's responsibility. That's why it's really important to write this down. Second, once you have written it down, it doesn't mean that your processes automatically work like this, and typically it takes some iterations and some time before your workflow actually reflects the way you actually work and want to work. And finally, maybe most importantly, our day-to-day problems have very little respect for workflows like these. Requirements change, deadlines shift, people go on holiday, that kind of stuff. And the trick here is to have a robust workflow in place, but to be flexible enough to deal with these kind of variability. That's absolutely essential, and their clear responsibility are key. Now, we made good progress, right? We have made a functional use case also usable, but we're still not able to really achieve those benefits I talked to you about. Cost reduction, flexibility increase. We first need to fix some other challenges. And that comes in this final phase, making it beneficial. And these challenges are also a little bit more abstract, perhaps. The first one is what we call circling back. What does that mean? That means that in this phase, it really pays off to invest in creating a community between users and developers. Why is that? Because we have all very long to-do lists, hundreds of points that need to be done at some point. And for our developers to decide what to work on first, they need to know how our users are using a technology. How are they using it, what are they working on, and what bothers them the most. Only this way we can prioritize all of this correctly. And that requires feedback. That requires feedback from users that tell us what works well, what should work better next time. And also the other way around. We need to keep our users informed. They need to know which are the new features that we're rolling out, how do you get trained for them, which technical issues are we currently facing. And this requires communication. And that might sound obvious, perhaps simple, but we have noticed that once your group of users and developers starts to grow, this becomes harder and harder to do well, and email doesn't cut it anymore. And that's where a community comes in, and you really have to think about how do you properly do this circling back. Next point, efficiency, excellence, balance. This is probably my favorite part. We of course need both, right? We need both efficiency and we need excellence, and we also know that these things are not necessarily compatible. If I want to improve my efficiency, sometimes my excellence suffers, and the other way around. In our development work, we often have a choice. Which solution do we implement? And some solutions are more excellent, some solutions are more efficient. And this image here on the left should visualize that a little bit. Let's say that we have tamed this snake-infested jungle swampland from before, and it has become this nice hilly landscape. And now the question becomes, which technical solution do we implement to get down this hill? One solution, stairs, right? They're great, they're robust, they always work. But yeah, a more efficient solution, obviously, would be to have a slide, right? Cheaper to build and easier and faster to use. With, of course, the drawback that once you're down the hill, yeah, it's hard to get back up. So that's something you need to be aware of. And what happens very often in development work is we have discussions, right? Developers discuss, do we install a more, let's say, do we develop a more excellent solution, a stairs-like solution, or do we go more for the efficient route that has some drawbacks? And these discussions are important because only this way you can basically get the right efficiency, excellence, balance. Now, in our experience, and maybe also yours, it's never just one or the other. Only installing stairs is way too expensive. Only installing slides means that you're stuck at the bottom of every hill. You need a mix, right? You need a mix between stairs and slides, slayers, I suppose. This is a big challenge, and the best solutions, of course, are those where you can increase both your efficiency and your excellence at the same time. That doesn't happen very often, but I have a very simple example I wanted to share with you. Code repositories. I talked to you about the challenge we were facing with a lot of MBS models we were creating, and, well, the messy situation that resulted from copying them around manually. We installed repositories. This is not witchcraft. This is a very well-known and often used solution. But we noticed that with this one solution, we could increase both our efficiency, so the speed with which we work, and our quality, so the excellence with which we work. So this is an example of a great excellence efficiency balance. Now, final point, and this one is decisive. It's called going beyond. So far, we have focused on bringing an existing process on the simulator. And by doing so, we have gained some efficiency. Some things have gotten easier or maybe faster. But now it's time for something new. Now it's time to ask the question, what can we do with the simulator that we cannot do in the real world? And that's what going beyond means. It means identifying what your new technology brings on top of how you're used to do things. And that really requires rethinking your usual processes. And for that, I would like to talk about Pitstop. It's an in-house development, and it is an example of going beyond. Why? Because Pitstop allows us, just with Formula One, to briefly interrupt a simulation, make a change, and keep on running without leaving the race, without having to reload your simulation. Why is this an example of going beyond? Because it allows us to do things we cannot do in real life. We can beam our vehicles from A to B, we can change components within seconds, and with a few mouse clicks, and that's where this virtualization use case really starts to shine. This is where it gets good. This is why we went through all this effort, and why we even started with bringing this use case on the simulator in the first place. Now, I would like to close with a small race to make this a little bit more, let's say, tangible. The race is between two contestants. On one side we have baseline, and on the other hand we have pit stop. And before I start the race, a few words about the goals. We want to do a damper change. So we start with damper set A, we want to evaluate it, and then change to damper set B and evaluate that. Now here at the bottom you see what that looks like for baseline. It's color-coded, loading time. In green we see simulation time. I've selected 10 seconds for each simulation. That's not representative, but it just, basically what is important today is what happens around those simulation times. Now, for baseline, this takes 5 minutes and 20 seconds. It's not bad, right? It's faster than we can do it on real vehicles. But let's go beyond. Let's see what it looks like for pit stop. And we notice a very different picture. A lot more green. We can do a lot more simulations, very short loading times. This is what going beyond means. Now, the race, I will start it. It will be a little bit hectic. We start loading models. That's what this hourglass stands for. Every time you see an hourglass, we're waiting around, right? On the right, we're a little bit faster, and within a few seconds now, we should be able to start the first simulation. There we go. First simulation, damper set A. We stop the simulation and we change the damper. On the left, we now also have our first simulation running, and there we do the same. After 10 seconds, we stop and we change the damper. Now for this, in this case, we need to go into our MBS software, which is Simpac, which is slightly more complicated, but the main difference is the loading times. So actually, on the left, nothing exciting will happen for the rest of this video. So we can focus completely on the right side, where almost now we should be ready with our damper change. We set the starting position, and there we go. This is the second simulation running with damper set A. And now we can start to play around. We have achieved our goal, right? So we can beam to another starting position within seconds. Let's do that again. Let's choose another starting point. So this is simulation number 4. We could do this a few more times. We still have a lot of time left, but that would be boring. So let's go to France. Let's tell road server, our road information server, to move to a test track in France. We select the starting position, and there we go. Simulation number 5. And we still have some time left, so let's change some more components. We also change the top mounts, and we change the bump stop. This is actually something that we actually do. So we use pit stop to do virtual damper application, and there's the examples you see here are representative of those. So what we have seen so far, let's see, simulation number 6 coming up, and now also on the left you see simulation number 2 coming up. So what we have seen is 2 simulations on one side. On the other side we have done 6. You can imagine that on a day of simulating, this type of speed really makes a big difference. And this is the difference between having a working use case and a beneficial one. So that brings me to the end of my presentation. I have shown you how much work is required to go from a functional use case to an actual beneficial one. And I've used this model for this. not only to provide some structure to my talk, but also maybe to give you a little bit of inspiration. If you feel yourself lost in a snake-infested jungle landscape, then feel free to use this model. Thank you.